This session is Hacking the Wireless World with Software-Defined Radio by Balint Sieber.
Thank you very much, David. Can you... Oh. Thanks, David. Is this working? You can hear me okay? All good? All right, great. Ladies and gentlemen, thank you very much for coming. My name is Balint Sieber. I like playing around with the radio waves. I am the applications specialist / SDR evangelist at Edis Research. And today I'd like to show you a couple of the experiments I've done sort of over the past year with software-defined radio. So I really like to teach people about all the wonderful things, interesting signals you can actually sort of receive and analyze with software-defined radio. I was fortunate enough to be able to help out in a lab environment teaching all these folks from developing nations earlier this year. And whenever I sort of travel, I always have also the fortune of teaching the local constabulary about software-defined radio as well. That was in Italy when I went to take that shot, and they just happened to turn up exactly on time. So today then I'd like to talk about restaurant pages, the radio data service and the traffic message channel, primary surveillance radar, and RFID systems. Almost everything I'll show you today has been pretty much done with GNU Radio, which is an open source software platform framework for doing DSP and software-defined radio. Does anybody know what this is actually a waterfall of, what sort of signals we're looking at here? Any guesses? We've got a hand here. It is, in fact, cellular. Yes, that's right. So right in the middle there, you can see you've got the, if I hop down here, sorry to the people on my right now, but you've got the 2G channels there, and interestingly, this FFT waterfall is running so fast that you can actually see the frequency correction bursts on the broadcast control channel, which are these sort of discontinuities. And you can see the traffic burst on the left there, and then different standards with wider bandwidths serving their customers. This is actually one of the other programs I like to use called Boardline. This is also that channel, series of channels there, and that's 50 megahertz of bandwidth. So in the past couple of years, especially with the advent of higher bandwidth buses like 10 gig and USB 3, you can cram a lot more samples down your pipe. So if that starts, then you can see the frequency correction bursts. You've got the broadcast control channels there on the right-hand side and the traffic on the left. And what's interesting is that at this resolution, you can actually see the symmetry in the broadcast control channel due to the nature of the GMSK modulation used. So there are some really, really cool tools like this one that really allow you to go in deep. This is the 400 meg band. I think this is like 100 megahertz worth of bandwidth flowing down through a 10 gig pipe using the X300, which is sort of a higher end SDR. If you want to go and kick it old school, this is an ASCII art DFT if you don't have any fancy graphics card or whatever, or if you can only remote in via SSH, then you can pop one of these open, and this is actually centered on the middle of the FM broadcast band, and it's 200 megahertz wide. So today, pretty much everything that I've done is using this little puppy here. You're welcome to come and take a closer look after if you haven't seen one up close already. This is the USRP B200. It's USB 3.0 up to 56 megahertz of RF bandwidth, and you can tune anywhere from 70 megahertz to 60 gigahertz. The B210 does 2 channels. You can do 2x2 MIMO, so it's a full duplex transceiver. So first with restaurant pages then. I'm sure you're all familiar with these pages. They go off when your food is ready, assuming, of course, it is ready legitimately. And so when you actually go and collect your food, you assume that the throughput at the kitchen or at the collection area is roughly the same as the order rate. But what happens if everybody gets paged at once, for example, just hypothetically? So I'm sure you've seen these sorts of units around. You want to figure out what frequency they operate on. You have a number of different options. You can either find the frequency on the device itself. It's often there on the label. You can look up the FCC ID on the FCC database. Or you can actually just use one of these software-defined radios as a spectrum analyzer and scan the bands until you find your local pager. So that is in fact one of the systems I was looking at. And it's quite strong because it's nearby, so it's easy to distinguish. Now, if you zoom in again, you can actually see that it's two different frequencies that either convey a 0 or a 1. This is frequency shift keying. And when you zoom in, you can actually see them changing there, and that is your modulated data. Now, what's interesting in this particular transition is that there's no long series of ones or zeros of the same frequency. This gives you a bit of a hint about the sort of modulation that's being used, the sort of line encoding. In GNU Radio, you can either write things in Python, write things in C++. Usually all the sort of computationally intensive DSP stuff is in C++, and the glue layer is in Python. There's also a GUI on top of that called GNU Radio Companion. It's a flow-based language, so you can chain together these signal processing blocks. This particular configuration is used to actually analyze this pager signal. So the first thing you do is actually find the signal, the frequency of your signal in your baseband recording, and then you use a particular block, which is the frequency translating filter, for example, to move it to baseband. So you essentially move your signal of interest to the center of the dial. And the next step is then to find what the deviation is from the center. So if you zoom in on that transmission, you can see that you have these peaks on the left and the right, and you simply measure what the frequency difference is between the left and the right peak, and that's your deviation. And that's important because when you go through this process of quadrature demodulation, which is actually turning those different frequencies into this sort of time series plot here, you want them to vary between 1 and -1. So essentially, this is transforming from frequency into this sort of time series data here, which will then be turned into the raw bits that you can then analyze further. The clock recovery block, which is used to actually convert the raw samples to bits, this one anyway assumes an input of 1 and -1. Now the next step also is to figure out how quickly your data is flowing through the system, because remember, we're approaching this completely blind. We have no idea of any of the particular specs of the system. So you can do this thing called cyclostationary analysis. It's actually quite a simple construction in GNU Radio. You put an FFT on the end of this, which shows you, instead of your waveform on a frequency plot, this actually shows you the periodicity of whatever signal has been coming into the system. So you look at the first peak, you read that off, and then you actually get the baud rate, which is highlighted in red in the top left. So that's actually the rate at which your bits are coming in. And now you know when to actually sample in your raw waveform to extract your 1 or a 0. And that's what the clock recovery block does. And in this particular graph, this is not samples anymore, this is actually 1s and 0s that you can then analyze to deconstruct your packets. So usually when they say, oh, the flow graphs are simple, I was telling a little bit of a fib there. This is that same flow graph, but I have shown all the hidden blocks. There's this neat feature that was put in there. You can click it and it removes all the disabled blocks. To produce all those graphs, I had all these scope sinks connected in the FFT sync. So they're sort of the graphical displays. So you can add a lot of different sorts of analysis in there just by dragging and dropping blocks. And those blocks that I was talking about before are highlighted there in green, and all sorts of analysis ones in the middle. So once you have your raw bits, you can put them into a program. I wrote this little one a long time ago that sort of lets you pick different combinations of line encoding, character encoding, and so on. And these are the raw 1s and 0s that are captured off the air. So the trick now is to identify how a particular pager gets paged. Now what's interesting again is that you have no long strings of 1s and 0. So there's probably some sort of line encoding going on. So with Manchester turned on, you can see that it halves the number of bits because it takes bit pairs and converts them into 1 or a 0, whether it's a 0 or if it's 0, 1, then it treats it as a 0. If it's 1, 0, then it treats it as 1, for example. And so once you've turned on Manchester encoding, then it looks more like a real packet. You have this preamble at the beginning, alternating 1s and 0s. And then if you want to confirm that it is in fact Manchester encoded, you can just move all the bits along one. And then it'll highlight in red when you get a violation, because in Manchester encoding you can't have a 1, 1 or a 0, 0. That's not part of the spec. So you can see that immediately you have a lot of bits that are highlighted in error. So that's a good confirmation. The next step then is once you go back to your offset of 0, You pull up another transmission and you start comparing bits to see what changes, and they're highlighted in green there. So you can see for two different pager units, the numbers are probably different, so those highlighted bits probably have something to do with the encoding of that ID. So anyway, obviously, when you are handed a pager, it has a number on it. This is presumably the number that they punch into their little unit to actually page you. I picked out 12 here. You can immediately see that in hex. Now there's another interesting byte on the end, which is usually your checksum. You can go through a whole series of different checksum algorithms. I did that. I started with various CRCs. It turned out to be a lot simpler. It's just a sum mod 255, and then that last byte matches up too. So that's pretty much the protocol. It's pretty simple. So if you want to modulate, then you just reverse the process, obviously. You need your preamble, you need your magic header, the pager number, the checksum. When you put it into your GNU Radio flow graph to go out of the transmitter, you want to then interpolate, frequency modulate to make it look like that raw baseband capture that we had before. Apply pulse shaping. I didn't, but ideally you should. And then finally, you resample for your transmitter, such as this thing. So this is actually the flow graph of the modulator. And your raw packet is just put together by some Python code. It goes through the interpolator, the frequency modulator, resampling, and then to the transmitter. So if you look at the output then, it looks very much like what we captured off the air originally, which is a good sign. So if we go and test it out, type in the number, there you go. So I actually played a prank on my boss. We all went out to lunch to this place after I had confirmed that this worked. And I said I was just collecting some more data. Instead, I had put an XML RPC server on my laptop and then connected my phone via Wi-Fi to my laptop so that I could actually trigger the pages from elsewhere while they were all just sitting around waiting for their food to arrive, under the assumption that it was just recording for later analysis. So I went inside, paged him, and he thought it was legit, and he went in, and there was a lot of confusion when he tried to get his food, and I had it on camera, and it was good. So that's one system. There's another system that uses more of a standard. You probably remember pages from decades ago, but you can actually decode this pretty simply using existing code. GNU Radio has a huge and very vibrant community. There are a lot of out-of-tree modules that you can download the source for and then compile it yourself and try it out. There's one called grPocsag, and I modified this a little bit, but that's essentially the block, and that does all the Pocsag decoding already. So again, this is the data that I captured off the air. You have your Pocsag frames coming out there, and again, it's a matter of then determining how the pager ID is encoded in that. So if we have a look at a Pocsag frame, actually here are a series of pages, you'll notice that there are varying numbers of idle slots and then some sort of a payload. Let's have a look at one. So you have your sync, you have a certain number of idles, and then you have an address and then some data. The data is always fixed, so somehow they encode in there what the pager should do when it goes off. But the address is interesting because you have 00, which is just padding. The next 4 hex digits are probably the sort of system address of the pager system, which is fixed. And then the last byte there is the ID of the pager. Now what's interesting about the address is that with Pocsag, you need to take the last 3 bytes, the last 3 bits off the address, and then actually that multiply it by 2, and that becomes your slot number. So that's how you determine what slot it goes in. And this is really neat because Pocsag was originally designed so that the address of the pager would be encoded in such a fashion so that the radio, the receiver in your little Pocsag battery-operated pager would be off for all of the other slots until it would wake up in the slot where it might expect its address to be. It would check it and then go back to sleep. And that way you can save a lot of battery power. Now, once you take this into account, you can construct your frame again. So you have your preamble, you have your sync, you calculate your address, you calculate the offset, insert the appropriate number of idles, you have a trailing idle if necessary, and then you add Pocsag's BCH forward error correcting code to each of those slots to create a correct frame. And so if you do
46, you can see it going out there. And 46 goes off, and then we'll do 39, and then we'll do 56, and then we'll do 83, and then 82.
So I went out for lunch with my colleagues,
and
so we had a
78.
number of pages to work with.
What's the point? How about 56?
So 56 didn't go off. I think it's because my preamble was a little bit short per the standard, not the longer one that they were using. But yeah, that's one of our hardware engineers. He's a good sort. Now the third system, I thought this was really interesting. It's actually reverses the roles, so the pager transmits. This is an example. And you actually put it down on the table, and underneath the table there's a little, I guess, RFID chip that it reads and then sends back to the restaurant where you're sitting. So when they bring the food out to you, they know where you've sat down, which I thought was pretty neat. This is Zigbee, so it's 2.4 gigahertz ISM. Now, there exists also this out-of-tree module, GRI EEE 802.15.4, that does, Zigbee has a complete transceiver in it, and this is quite an elegant solution. If you actually run it while you put the pages down, then you get those frames out, put it into Wireshark, there were the 2 pages, get the numbers, turn them into hex, what do you know, they're in the payloads. The table, I actually went to the kitchen and looked at their screen and I saw what table we had been sitting at, which is there on the bottom left, and that's also there. So that's the third system. So this is all pretty doable with open source software and just one of these software-defined radios. Now, what's interesting is that when pages go out of range of the system, usually there's a beacon that goes off periodically. They all get angry and light up and make noises. So for whatever reason, if you wanted to take a pager hostage, you could recreate the beacon, something like this, and then take it away. That's pretty benign, but you never know. So that's pages for you. The next thing is the radio data service. You've probably seen on your radio, whether in your car or some sort of another receiver, the song name come up in the station and that sort of data. That's sent digitally over the FM broadcast band for the channel that you're listening to. So this is actually an example of some stations, and I've zoomed right in here in time so you can actually see the subtle variations in the FM carrier that's being modulated by, for example, somebody talking. I think that's voice in the middle there, so you can see that modulation, which is kind of nice. If you look at it actually in a video, you can see all the channels there being modulated by whatever audio information they're carrying, and if you look even closer, you can actually see the 19 kilohertz pilot tone, which is injected to enable you to have stereo FM, and then other subcarriers beyond that, like RDS. If you zoom in further, then you can see that as a video. It looks pretty neat. Now, so RDS, you get things like the station name there. This is not audible because it's filtered out. It's on a high subcarrier. It runs at this odd baud rate. It's phase shift keying, and there's another out-of-tree module for Gooding Radio that you can use to decode and modulate. So just as an example, this is Sutro Tower in San Francisco. It has a number of different FM radio stations broadcast from it. And if you run it through the demodulator, you get something that looks like this. On the right-hand side there, you can see the baseband of that radio station. On the left-hand side, you can see all the RDS data being decoded in real time. On the bottom, then you have your sort of standard readout of the station name and the song name and so on. And then you can see all the subcarriers there once you do the initial demodulation step. Now, the one that I was interested in was RDS, which is that one that's highlighted there. It's a couple down. So you've got the left plus right, which is the mono audio, then the first sort of peak, which is the pilot tone. You've got your left minus right difference channel that's used to recreate the stereo audio, and then you have RDS. So RDS contains all that information that I mentioned before, but it also contains the traffic message channel, which contains compact representations of traffic events in your area. So it sends out the event, the location, and the duration, and some other data as well. So you can have congestion, accidents, roadwork. So this is an example you can see here on the bottom side. There's roadwork reported, and up the top there's some congestion along, I think it's 580. Now, this is actually from the nav unit in my car, and I wasn't sure whether it was coming from RDS or whether it was coming from the Sirius satellite service. So what I did was I got one of these, and I blanketed the entire FM broadcast band with white noise to knock out every single radio station to see whether or not it would still update. And as it turned out, it still kept updating. So then I blanketed the entirety of Sirius with white noise, and what do you know, everything disappeared. So my initial assumption was that it was coming through FM, but it wasn't. But the data flowing through both services is exactly the same, because I could look at information coming from the RDS decoder and it would sort of match roughly what was here. Now, if you actually filter out all of the things like, well, actually, no, this is unfiltered. So you can see the subcarriers there, and then suddenly information starts coming out. You've got, once you filter out congestion, things like that, you're left with things like current temperature, and you're left with other things like probability of rain, some sort of weather forecast. And I thought, well, maybe you can plot temperatures over time and produce some pretty graphs. But the issue is I found out that once you filter out all these locations, and even for these locations as well, the locations are encrypted, and there's no public source for the US. For Europe, actually, a lot of countries do publish this information. And this original software out-of-tree module for GNU Radio was written, I think, by some people in Italy. Now, apart from receiving, of course, GRRDS can also modulate. You can actually program RDS information to be sent, so you can try that out and create your own station names, for example. There's that one. And it's just the laptop and one of these radios in my car. And this is actually the flow graph that's used, and you can see we were receiving before, but this baseband subcarriers look exactly the same as what we had before, but just without the noise, because we're synthesizing this data ourselves. Now, as I said, the location codes are encrypted. Everything's 16 bits. The encryption keys are 16 bits. And what happens is there's one key that's chosen per day, and there are 31 possible keys, and these are stored in the devices themselves. This key, as you'll see in a moment, has an ID, and that ID is broadcast continuously for that day and then changes the next day. So what you can see here, oops, let me just go back, is this is just the information coming through in real time, unfiltered. And from this, we need to select the interesting thing. So I think there you can see it says ENC ID 27. I can't quite read that myself. Yeah, so that was the key ID for the day. And then what I noticed was, there we go. What I noticed was, as I said before, these temperatures were coming through. But as I tracked them per day, it didn't look like they were varying as temperatures would. So there was something else going on, and it just happened to coincide with the event that in the public lookup table mentioned that it would be a current temperature, but in this case it wasn't. So I would track those, and I saw these patterns begin to emerge. So there were always 3 unique temperature reports per day. And so these group of 3 would always be the same throughout the entirety of one day, and then they change. But you would actually have these event IDs always be the same. So there would always be some temperature report, and the temperature value would always be the same throughout a day, and you would always have the event be similar too. So once I saw these patterns, then I thought, well, maybe there is an in after all. Maybe I won't be graphing temperatures, but there might be some way to get around this encryption. So once you track the temperatures, then every day you will see 3 unique reports, and these are 2 of them. So for this mysterious location that doesn't probably represent a real location, you have this unique quote-unquote temperature value for that day. And then the next day, you might have exactly the same location, 3 locations, but a different temperature. So what you do then is you construct this sort of table. You have time and days going across the top from left to right. You have your key IDs, which is that first row. This is, they represent the actual keys, and that's hidden to you as the receiver. And then what you do is you basically build this lookup table yourself where given a particular key ID and that group that you're in, you build a lookup table and then proceed to the next day. And you can keep matching them as long as the periods are the same. So you can see in the first two columns, you have P1 and P1. So that means you will have the same event IDs, but different temperatures. So you know how to match them, the pairs across the day. And you keep doing that per day until you build up this lookup table. And then if you analyze it from a security standpoint, obviously 16 bits is very short. You can probably do some sort of exhaustive search. And then if you have these singular events that occur, you can probably speed things up as well. So instead of having congestion, which occurs during peak hour all over the place, you just want to look for very unique things. So for example, an object on the road, who knows what that could have been? But you can use that to your advantage. So what you do then is you take that lookup table that you built, you take these unique events, and you basically want to discover what the plain text location was that was encrypted with this unknown key. And then you want to also discover what this mysterious key is as well. So what you do is you have this pair that you've recorded from the air. You go through every possible plain location code and every possible key, and then see whether that matches your recorded data. So you build up this enormous pool, and then you start filtering down based upon all of the other records that you've got. So now that you've got all the possible keys for that one day, you can try that for the other two locations to see whether your potential key plus your potential plain text location for that particular possible location matches what you received. And you go through and you iterate and you filter and you remove the invalid entries. Another way of looking at that, this is like that you have your lookup table, you go into this iteration loop, you have your potential pool of plain text locations, your potential pool of keys, and you keep removing from it every time you get an invalid result when you try and compute what you received over the air. Now, despite that it's 16 bits, the nature of the algorithm means that you have a lot of matches to begin with, so you do need to look out for these unique events. At the end of the day, though, this is what you get. I would basically record data every day. I would check and record the key ID and that group of 3 that would come down. And then I've got some unique matches for various key IDs. Some of them you can see there are still a lot of possibilities. I haven't recorded all of them because it's really completely random which one comes down. I think there are 3 or 4 left that I haven't seen yet. But the interesting thing is because of the nature of the algorithm again, you don't need to have all the keys for one particular key ID. You can actually just query it for a location code that's encrypted, and despite the fact that it has multiple keys, you can still get a unique match, which is kind of interesting. So again, unfortunately, singular events are usually terrible things like vehicles on fire, flooding, an object on the roadway, but I guess they happen and you can make use of that. So as I said, it still works even though you have multiple keys available. So that's RDS. Now let's move on to some aviation radar. You've probably seen at airports the radar receivers like this. This is actually the primary surveillance radar dish, the really big one. And then on top of it, you have the secondary surveillance radar antenna. Now with primary, it operates like probably you've seen in movies and computer games or in real life or photos where you have this radar scope and it spins around and it sends out a radio wave which bounces off metallic objects and then comes back and is received by this big dish. Now, because it's this sort of passive system, you get very, very high losses in the radio waves that's sent out because they're just going to be reflecting off these small targets. The secondary system operates differently. You send out this radar ping, and then you have a transponder on the aircraft that receives that ping and then replies actively itself with a message saying, yes, I'm here, this is my flight ID, or this is my altitude. Now, with primary surveillance radar, the way it works is if you're looking at it in time, from left to right there, you have your main bang, which is transmitted out, and then the radar switches to receive mode and just waits and listens for these pulses to return off any potential reflectors. And this is happening very, very quickly. So it sends out a pulse, listens, sends out pulse, listens, and this happens, you'll see in a moment how quickly, but as it spins, it's doing it many, many times a second. So these echoes are what's interesting. Now with the active system, which you've probably heard about before, for example, ADS-B, which is on top of Mode S. The aircraft is independently broadcasting this information regularly, so position, heading, altitude, vertical rate, flight ID, and so on. And there's obviously been a lot of work done here. It's all unencrypted, so you can receive it all. Things like 747s, aside from just this particular radar system, have a huge number of other radios on board. So it makes someone like me really excited. And if you look carefully next time you fly, probably quite soon, you can try and spot all of the antennas. Usually they're above and below, as you can see there. So this is an example of a Mode S frame. It uses pulse position modulation, so it encodes data as a series of pulses. And you can see here it actually uses Manchester encoding like in the pager system, depending on whether it's a 1 or a 0 or 0 or 1, how the pulses are positioned in time. That converts into your special binary bit that you can create a frame of data from. And when you actually visualize this as a GNU radio receiver, you can see that there are a hell of a lot of them in the air at any one time, and you have that preamble kind of at the beginning there, and then your payload after that. There's a whole, an extra talk that you can do about this, but at the end of the day, you can do cool stuff like this. This is an animation of planes on the West Coast, around San Francisco. When transponders broadcast bad information, then you get pretty effects like these. And you can build up interesting trails of flight paths over time. This is San Francisco Airport. I just went there with one of these software-defined radios, and you can watch parallel landings, for example. Those green plane markers will turn red when the nose gear hits the runway. And there goes one. There goes the other one. And then you can also look at things like takeoffs. I think this is a Virgin America flight there that's highlighted in the bottom. And that's, I've sped this up a little bit, but you can see the actual video of it there in the bottom right, speeding up and about to lift off into the air. And it will go from red to green once it's off the ground. There you go. And it's actually following pretty much the same flight path as you'd expect as another plane that just took off prior to that. And look out for the plane in the top right. It's coming. There it is. That's okay, though, because they're on wildly different altitudes, as you can see. Now, because you're sending altitude information as well, I've created the system that live streams through Google Earth in your web browser. So this is that exact same takeoff, but in 3D, you can sort of pan around and see what's going on. Bit of fun, all the other planes in the area. You've got San Jose and Oakland Airport. Like there's that 424 that's landing in Oakland. And then on top of that, you can also do the virtual cockpit view, so you can be in the pilot seat and experience what the takeoff would be like, for example. So it's the same thing from the point of view of the airplane, and then it goes up into the air and swings around. And that looks pretty cool on landing as well. So this is landing. This is when I was coming back from the East Coast. This is obviously sped up. It would be nice if landings were this quick. But here we go, boom. And then come around, wait at the holding point. Google Earth did some really weird stuff with the burnt out fuselages of planes. I'm not quite sure what was going on there, but we pulled all the way into the terminal, as you can see. It's kind of neat. This is actually the system running in Sydney, Australia, which is where I'm from. In addition to Mode S, aircrafts also transmit a lot of quote-unquote text messages, which is the ACARS system. Each of those balloons is one of these messages. It can be messages to flight, traffic control. It can be automated status reports from the engines and so on. Flight information and flight paths, as you can see, being drawn there in white. I added a bit of an Easter egg whenever there's a report of a broken toilet. Then it throws up one of these icons. And then you can also see these flight paths going into Western Australia and also into Asia. So this is all the active system. This is when the transponder on the airplane is transmitting. What about the primary system? Well, in the Bay Area, there's this particular ASR-9 primary surveillance radar near Moffett Field Air Force Base. And that's what it looks like. It's as you would expect. I went out there with a B-200, just to sample the signal and see what I could find. Previously, I'd played around with an Atheros 5 gigahertz Wi-Fi chip that has dynamic frequency selection, and there's this radar detection mode, and I thought it'd be interesting to sort of hack on that and then try and get information about the radar from the Wi-Fi card. And I found in Sydney, I was listening to the weather radar, and so some patches enabled me to sort of extract that information, but I wanted to recreate that with a general software-defined radio. So this is the B200, this guy, and remember, throughout all these experiments, all I'm using is this and that whip antenna, which is a highly non-ideal setup. If you consider the gain of that omnidirectional whip antenna versus the gain of that directional radar dish, it's absolutely enormous. But I was just curious to see what you could find. So as the radar rotates there in the bottom right, you can see that there's a huge increase in amplitude. The left-hand scope there is triggered by every pulse being sent out by the radar, so it can pick them up even if it's not pointing at you because it's so strong. And then what you'll see is that you have these little bumps in amplitude following that main burst. Can you all see that in the left hand? I'll play it one more time. And I thought, well, hang on a second. Surely that can't be radar returns. I mean, okay, maybe with the whip antenna, you can pick up the ground clutter. But I thought it deserved a little more investigation. So if you actually look at one particular pulse, you can see that on the left-hand side. That's the main bang. And then you have your echoes, and you can see them come back at the bottom. Now don't get too excited. This is just a little whip antenna, so we're not going to pick up anything that's hundreds of kilometers away. But this is going to be stuff that's relatively close in and usually classified as ground clutter, which is like large buildings and so on that will reflect the radar signal quite easily. If you're ever in the Bay Area and you want to hang out up on a hill by a water treatment facility, which is the best vantage point of the radar, feel free to come along. We were out there last Friday. Some of my friends came out to help, which is really lucky because the Thunderbolt port in my laptop just happened to break, and so they sacrificed their hand pushing it in to establish the link to the 10 gig network card, which is then connected to the X300 USRP there. So we've got some antennas sampling the signal, recording it at 100 megasamples to RAM disk. And if you've seen any of my previous presentations, this was such an incredibly similar scene to when my friend Matt Robert and I used to go in Sydney up to the park that overlooked the airport, and this was this kind of setup that we had there in the night, receiving the Mode S frames. But if you look at the raw data then, I thought, well, let's begin processing this and see what we can pull out. So I recorded the radar as it spun around, and you go through a series of steps to try and figure out how to map that and see what the radar can actually see and what your radio can see. So the first thing is you go through and you basically plot a histogram of all of the sort of average windows of magnitude throughout your file to determine where you're going to draw some lines, draw some thresholds. If you look at that on a log scale, you want to basically exclude the noise floor. So you would pick some threshold there because the vast majority of samples that you get in are going to be noise. And that's going to be that huge peak on the left-hand side. Once you filter that, then you focus in on the right-hand side of that, and then you want to basically pick a threshold which will only sample out the bangs that come out from the radar. And this is important because you want the receiver to synchronize to these bangs. And then if you look at that on a log scale, you can see that they're not going to happen that often, so it's probably going to be all up in the right-hand side of the distribution. So you pick some threshold there. The threshold is you would pick from the x-axis because it's a histogram. And then once you do that, you can actually start looking at the width of these pulses. This is a histogram of the potential widths, and you can see there's a peak there. So you would tell the detector to sort of focus on pulses that have this kind of a shape. And basically you're teaching the detector what these radar pulses will look like so that it can synchronize and then try and track any returns. Once you do that, you can see the actual bangs here, they're overlaid on top of one another. And you can see this nice sort of pattern come out. There's this nice sort of hole in the middle there. It's like an eye diagram. You can see that the pulse initially comes up. It lasts for a certain number of samples because we're sampling at a very high rate, and then it drops down. And then you can see some interesting patterns to the right there. You overlay some more and it becomes a bit thicker. Log scale, it still looks pretty. Once you actually look then and draw over time the separation in samples of these pulses, you get these two lines, which is interesting because you'd expect with a radar, it would send out the pulse and then wait and then send the next one. And this would happen at a very regular interval, one particular pulse repetition frequency. As it turns out with these radars, they operate in this thing called dual PRF mode. So it'll send out pulses at a particular rate for a certain number of transmissions, and then it'll switch to this other one, and it'll keep switching back and forth. And this is to resolve ambiguity. And you can very clearly see that coming out here with these two lines. The outliers are just spurious detections. All you're really interested in is that you've got these two emerging patterns here. If you draw a histogram of that, then you can very clearly make out the two pulse repetition frequencies there. One is, I think, 975 hertz, and the other one is 1,250. And that's basically the rate at which it's sending out this bang and then waiting for the replies and processing it. You can then plot that over time. You can see this is only tracking the strong pulses, so you get that point at where the radar begins to face toward you. You receive a whole bunch of stuff, and then it dies down, and you don't detect it after that. But once you actually put in all these parameters and set your thresholds, then it begins tracking continuously, even the weaker ones. And then you get this sort of pattern. So this is 6 revolutions I was able to record to RAM disk. I think that was about 6 gigs of memory, and if I went beyond that, my whole OS would die. But you can see as it spins, your amplitudes change, and this is the pattern that you would expect. Again, you have your 2 pulse repetition frequencies there, and because of the clock not on the crystal on the SDR not being perfectly synced to the clock that the radar is using, I'm guessing that's the explanation for these little gradients there when it's selected one particular PRF, and the distance between each pulse is not being constant. So what does it look like actually when you have the system synchronized? The main bang is going out there on the left, and then you have the very closest returns coming back, and you can see them changing there to the right. So the system is synchronizing to that first transmission, and that's usually the strongest one there that it's picking up on the left-hand side. Now this looks all nice when you animate it like that, but let's turn it into a bitmap, into a raster plot. So you can see down, going down on the vertical axis, every scan line will start with a detected pulse transmitted from the radar. And then it just starts sampling after that. So on the left to right, on the x-axis, it's just time. And so what happens is once you build up this plot, you can actually see returns coming back from various objects, large objects, because we're only going to receive stronger signals with this. And these sort of patterns coming out. So if you look a little closer, it looks quite interesting. This is all, remember, off the air, just synchronized to when a pulse begins, and then it starts recording after that. And you get interesting shapes. I wonder what that could be. What's this dot that's further out? And so the next step is to actually put that on a map. So once you do a polar unwrapping and then put it on, say, Google Maps, you can see that it perfectly aligns with large physical features in the Bay Area. So let's have a closer look. The radar is centered there in the middle of the screen. You've got a lot of ground clutter from the buildings and hills immediately around you. And then I saw these odd sort of stippled lines appearing that are actually enclosed in red there. I was wondering, what is that? Well, if you look, you have power lines running across the entirety of the Bay Area, and that's what was reflecting the signal. And then you have the San Mateo Bridge further along, and so on. Now, once you actually record lots of different rotations, revolutions, you can actually take the first one, map that into the red channel, take the last one, map it into the blue channel, and pick one in the middle and map it to the green channel. And then what you'll see is a lot of all the static stuff will appear in white, but anything that's moving will appear in an RGB triplet. So nothing particularly interesting happened in this one, but in this one you can see that there's a triplet like that. You see that? So that's actually a target that was moving through the duration of my recording. Now, based upon the speed and so on, it was pretty slow. It wasn't an aeroplane or anything like that. The next stage is obviously to use a directional antenna and see if you can get a return off an aircraft, but the radar cross section is going to be pretty small, so you need to use a bigger antenna basically. This one here, you've got another sort of triplet. Once you unwrap that, you get the polar plot. That little triplet's up there, and then if you put the map underneath, You can kind of barely see it there, but it's probably, it basically lined up with a road, so it was probably a truck moving along a road based upon the speeds that I calculated. It was like 40 kilometers an hour, something like that. This is actually from my hotel room upstairs. You see planes coming, and I thought it might be cool to record stuff. The issue is that the primary surveillance radar at the airport here is in the bottom right. The Mandalay is up there. If you sort of think about it, the system won't work because when the radar points at the Mandalay at my antenna, it's going to flood it, A, and B, if there's something else that might be sort of bouncing off, then that'll be following the same trajectory. So that won't work. Really, you need to have targets that are further out. And you can actually visualize this. You can create these distortion maps. The top is actually when the radar and the receiver are at the same point. What you're interested in looking at is the 2D there on the right-hand side. If you offset your receiver and your transmitter, which is what I've been doing, then you can see some, I don't know if you can see that, but there's some very subtle shading there. The red and the blue are the Y and the X offsets that you need to use to compute your distortion map when you actually look at the returns. But if you exaggerate that and you normalize it to the size of the thing, the actual bitmap there, you can see that there are some significant changes that you need to apply spatially to your data to see the world as if your receiver was actually at the transmitter, which is not the case in this kind of bistatic setup. Anyway, I saw these triplets emerge from upstairs. I haven't unwrapped them and put them on the map, so I don't know what it is. But I also saw this one particular pass with a lot of extra returns close in. But there are some interesting features that pop out. So I'm just going to rush through this because we're running out of time. But you're probably familiar with Fast Track or Easy Pass. It's a traffic toll tag that's used to bill you when you use certain tollways. There was this excellent presentation in a previous year here at Black Hat, and that inspired me a great deal. I saw these antennas and I was wondering what they were for in San Francisco, so I went and recorded the signal. I actually went and looked very inconspicuous and not suspicious at all at the toll booths at the San Francisco Golden Gate Bridge, recording what I found there. And this is what I found. So you have this wake up, you have the preamble, you have the payload, which again is pulse position modulated like Mode S, for example. And then you have this backscatter carrier that runs while your pager should be, not the pager, the fast track tag will send back through backscatter modulation to the reader. So I'll skip that. You can use an antenna as both a receiver and a transmitter. So this is the GNU radio program that runs. You have your carrier wave there. When you hold up the fast track tag, it'll reply with a response, and you can see that modulated on the backscatter. Right there. And that's actually what's read out, and that contains your ID. And this is all, again, unencrypted. So if you look very carefully in this video, that's what's being received there. And you can see you've got the large series of pulses at the beginning, which are the transmitted payload, and then you have that small bit of squiggly mess up the top, and that's the backscatter modulation, which then is processed to extract those bits and identify you. And if you actually try to
fast track tag there, and I'll attempt
use an antenna, then you can actually just, I've put one behind the dash there, you can walk around and read everybody's tags. That's the flow graph. We also tried to look at the wireless entry and keyless authentication with the Prius. That's a USERP that does dual channel recording. One of them we did for UHF for the actual remote. The other one we used the low frequency for the broadcast from the car itself. This is what the broadcast from the car looks like. You can very clearly see the data modulated there as pulses. Again, for the UHF for the remote, there's pulses coming back. You can simply turn that into ones and zeros and look at how the authentication works. I'm assuming the crypto is pretty good. And you can also use Boardline to do this sort of dual channel FFT. So the blue is actually the low frequency component, and the red is what's coming back from the remote. So you can actually view these on top of one another and see how they align in time, which is pretty neat. And that's the flow graph for that one. Again, you can look at badge authentication. This was in our building. Just hold up a loop antenna and you can see the transactions going on. This is actually using backscatter like the fast track. So you can see there the reader is sending out a packet and then it's having a carrier, which then the badge modulates. So just to finish up then, you may have heard about the ISE3 reboot project. I was fortunate enough to be part of this as sort of the radio guy. In a short summary, NASA sent out a space probe over 36 years ago, and it's been heading back toward Earth. Some people thought it might be interesting to talk to it again and fire the thrusters and bring it back into near-Earth orbit, and turn the science instrumentation back on so that it could be made available for public science use again, for STEM education and so on. We went down to Arecibo with some SDRs. The Arecibo radio telescope is the single largest sort of static dish in the world. The scale of the place is just incredible. We got to go up onto the platform to see how we were going to integrate the new transmitter. This is actually in the receiver patch panel room. We have the SDRs hooked up into the patch room there, and this was our first detection of the carrier from the space probe. The pointing was off because the ephemeris data that's used to actually locate the probe in the sky was stale, but after a bit of searching, this sort of weak signal, you can just see the line there. Time is going down the y-axis. Frequency on the x. Once you do a bit of pointing, you can see this is going to be radio again, a huge increase in the signal-noise ratio, which was great. But telemetry had been turned off, and so our first task was to turn telemetry back on to actually assess the state of the space probe. So this is the commands are being sent out, and just to make sure they are actually going out into the sky, I had a B200 there just receiving the signal on the laptop to make sure they were leaving the dish and heading up toward the space probe. And this is what happened. So we managed to send the first command up to turn telemetry back on, and it was wonderful waking the space probe up after such a long period of time. A lot of credit has to go to the team. There's a lot of sort of NASA old document dumpster diving that was done to try and figure out how to talk to it and how to interpret everything. But this is actually the telemetry now coming down on both transponders on the bird. So that was great to turn it on. Then there was process of decoding that and so on. And right now I've got the stream running live from my website. I've published the source code so that you can interpret it, and people are sort of getting into that. So once you run that software that I put together, it actually shows you what all the values of the different telemetry elements are. We were trying to fire the thrusters to get it back into Earth orbit. This was the state of the propulsion system, so it would be a little bit like mission control. It was based at NASA Ames in the old McDonald's there that had been converted into a place called McMoon's, and that's where mission control actually was. And we'd sort of look at this and make sure that the thrusters we were going to fire were the right ones and they'd fire for the right amount of time and so on. This is actually plotting the telemetry that's coming down. You can see, for example, the transponder lock, and I think the bottom left and the top left are the values from the accelerometer. So every time a thruster fires, you should see a matching sort of peak pulse on the accelerometer. Unfortunately, though, it looked like although there was still a lot of fuel left on the probe, the pressurant that actually forces the fuel out of the tank down into the thruster, that pressurant, which is nitrogen, has just disappeared. So unfortunately, as hard as we tried, we couldn't seem to get enough thrust to change the orbit. So it's going to do a lunar flyby on Sunday, I think, or Saturday, and it'll continue on its merry way. But we tried, we've put it into science mode, and we're going to track it every day and turn science instruments on, and there's a magnetometer and various other science instruments that we're going to receive and see what we can actually get from it. This is the team outside McMoon's, and thank you very much.